Our first speaker is our Francesca Starita, and she will be discussing again about threat learning and specifically how threat learning shapes kinematic patterns.
Hello, can you hear me? Also at the back? Yes? How are you? Are you still awake? Yes, hopefully. So this is going to be the last talk. So I'm still going to talk about threat learning, but I'm going to talk more about overt behavior and action. So how threat learning shapes action. So we've seen already how threat learning shapes the excitability of the corticospinal tract or of the motor system, but here we're going to look more at overt behavior. So again, just to give a recap, when we learn that an intrinsically neutral stimulus is a predictor of something aversive, the presentation of these intrinsically neutral stimulus elicits a series of responses that are called conditioned responses. And this conditioned response can be of different nature. So they can be psychophysiological responses. And we've seen a response, for example, skin conductance response, or also changes in map amplitude. They can be changes or responsive of changes in subjective experience, or they can be a change also in overt behavior. So here you can see an example of this. So these two characters maybe have seen something dangerous or a cue that predicts something dangerous in the environment, and they show a coordinated pattern of response. They start shivering, so there is a change in physiology, but they also start to either move, this guy is running away, or they may freeze. So we have a coordinated pattern of conditioned responses that's elicited by cues that predict danger in the environment. And here in particular, the question that we wanted to answer was whether Pavlovian acquired threat value transfers onto motor control. So how threat value acquired through Pavlovian learning influences overt behavior. And what we did was to characterize changes in movement kinematics after fear learning or threat learning at the beginning, during, and at the end of a movement that we have to perform on the conditioned stimulus. And to do so, we have a task that it was similar to the task that we've previously seen during all this morning. So here in particular, we had a so-called baseline phase. And during this phase, participants had to perform movements, reaching movements with the mouse towards a target that appeared on the screen. So they just saw a colored dot on the screen, and they have to move the mouse to reach the dot. And to make it a little bit more interesting and also functional to the next phases, so the dot could appear in 3 different positions on the screen, and it could be colored of 2 different colors. And during the movement, the reaching movement, we tracked the mouse, the movement of the mouse during the task in order to characterize the kinematics of their movement. So after the baseline phase, we had a Pavlovian threat learning phase, in which this time participants do not perform any movement. They just observe what's happening on the screen. And again, on each trial, they see one of the 2 color dot appearing in one of the 3 positions. So they just see a dot. It could be pink or yellow. They don't do anything. But what happens is that one of the 2 colors predicted the arrival of a shock. And the shock was delivered on the non-dominant hand. And again, it was calibrated to be highly unpleasant, but not painful. So here participants were asked to learn the association between the color dot and the shock. So learn which color is going to give you a shock. And during this phase, we recorded skin conductance response. Then after the learning phase, there was a test phase in which participants repeated exactly the task they did before. So again, they saw the 3 different color dots. On each trial, they saw 1 dot, and they had to reach the dot with the computer mouse. Again, we tracked their movement with mouse tracking, and they just performed the reaching movement. This time, no shock was ever delivered. Okay, so they performed the movement under safety. There is no danger there. And the question was whether after having learned that one of the two dots was associated with a shock, so for example, the fact that the pink dot was associated with shock, we wanted to know whether their kinematic of movement would change. And here are the results. So here is the result at baseline. And what you see in these three different graphs is different kinematic parameters. So here you see the peak velocity of the movement, the peak acceleration, and the peak deceleration of the movement. And here is the change in each parameter as a function of the position of the stimulus. So whether the stimulus appear in a low, middle, or high position on the screen. And you can see that the velocity of the movement, as well as the acceleration and the deceleration, is modulated by the position of the target. So it increases the further away is the dot on the screen, or the longer is the mouse movement they have to perform. So this confirms us that participants are actually doing what they are asked to do. Okay, the movement is modulated according to the position of the target. But the movement at baseline is not modulated by the color of the stimulus, because no association with the shock has happened yet. Then we go through the threat learning phase. We measure the skin conductance response, and what we see here is the modulation of the skin conductance response as a function of the position of the stimulus, and here whether the stimulus was a CS plus, so predicted shock, or was the control stimulus. And you can see here that the skin conductance increased for the CS plus stimulus relative to the CS minus, so when the stimulus predicted the shock. And instead, it was not modulated by the position of the stimulus. And what it suggests us here is that indeed there was a conditioned response, or in terms of autonomic modulation, that was produced or that was acquired during the Pavlovian learning. So our participants indeed learned that the CS plus was the one predicting the shock. And here I've added the results of the test phase. Okay, so again, we look at the kinematics, and we can see that also at test, the velocity, acceleration, and deceleration of the movement was modulated by the position of the stimulus. So participants are still performing the task we asked them to perform. And here, there is something else that's happening this time. So after threat learning, what we see is that the peak velocity, acceleration, and also deceleration are also modulated by the fact that that stimulus was a CS plus or a CS minus. And in the velocity, acceleration, and deceleration in particular increase in response to the CS plus. And remember that here they're performing the movement without any danger that's present. Okay, they're not receiving any shock. So despite that, there is still a modulation in the kinematics. And the results that I show you were also replicated in a second experiment. So we see a similar pattern. Also, we did a little manipulation in the task. So this time there was no baseline phase, but then conditioning and test were the same. And we still that although there was no baseline, meaning that although you never performed the movement on that stimulus before, although you never acted on the stimulus before threat learning, you see that threat learning still elicits a modulation in kinematics that's similar to the one we saw before. So again, an increase in velocity, acceleration, and deceleration when acting on the CS plus relative to the CS minus. And what's also interesting is that when we looked at correlation between the responses during the threat learning phase, so the skin conductance response during threat learning and the change in velocity, acceleration, and deceleration during tests, there is a correlation between the strength of threat learning, so how much your skin conductance increased for the CS plus relative to the CS minus during threat learning. This correlates with how much, how faster you went during the test phase, how much more you accelerate, you speeded up your movement and also the deceleration of the movement. So it suggests that there is a direct relationship between the strength of threat learning and the consequences that this has on movement. So just to wrap up, so we can conclude that Pavlovian acquired threat value does transfer onto motor control, and in particular that threat learning changes the kinematics of the action that is directed to a stimulus that has acquired threat value, and in particular increases, so the direction of this change is of an increase in movement vigor. And these changes in motor control emerge even in absence of an actual threat, so there was no shock there, okay? And even though the action also have no effect on whether you're gonna get a shock or not. And you could think about these in relation to some more clinical aspects or pathological manifestation of, for example, anxiety disorders, that you are doing behaviors that are related to something that you think it's threatening, even though there is no threat present. And also we observe that there is a direct relationship between Pavlovian acquired threat value and motor control. So the changes in action kinematic correlated with the strength of threat learning. And again, these may suggest that if you think about pathological manifestation or more clinical aspects, again, it may be that the stronger was your learning, or the more traumatic was your experience, the more likely you are, or the stronger will be your change in behavior. So that's it. It was very short. I hope you were still awake. Well, thank you. Thank you for listening. Thanks to all the people of the Model Lab and also to the BL Foundation for finding the research. So do you have, yeah. Okay. Yes. Yeah. Yeah. Yes. And I think the cerebellum is, yeah, definitely. Yeah. Interesting to look at. Yeah. Yes. Do you have any questions? Yes.
Thank you.
Good.
Quite nice. I will read the paper. I was just wondering whether you would expect this increase in movement or legal movement be something quite general or related to a specific task. Imagine that your movement is, I don't know, you have something very you have a signal and you have to approach this offline. So I just wonder whether you would have expect similar increase or anticipate the decrease of it. So, or would you consider this your result to be an instance of some tendency of the model to be let's say task specific or related to the contingent?
Yeah. Yes. Yeah. That's very.
And I just wonder whether you are thinking to explore more movement or what. That's cool.
Yeah. So yeah, that's a very good question. I expect, to be adaptive, your response should be related to the conditions in the environment you're facing. Also, for example, as Daniela was saying, how far is the threat, or whether you can actually escape or not. So Valeria before was saying that rats freeze when they cannot escape. So yeah, so in this case, I think that's the results we found are partly related to the task that participants were performing, because in this case they were they had to reach to the target So maybe if it's something dangerous you want to do and you cannot not reach, you can have to move towards it, you want to do it as fast as you can in order to go and maybe go back to safety. What's interesting is that here there was no shock was delivered. We also have, well, we've done further manipulations on that. So even when we detach the electrodes from the participants, so they're sure they're safe, we still see the increasing vigor. So they still move faster. But I mean, talking about the map results, we find an inhibition of the motor system. So maybe you wonder how the two can go together. So
if you make the condition more similar, you will expect something. Because there is a literature of function avoidance movement towards points. That's quite, I would say, full of mixed results, because they tend to consider approach different things and avoid different things. So
yeah, one thing is approach withdrawal or approach avoidance can be many things. Yeah.
So, and what I think is quite interesting is that the motor system that you guys showed that it's consistently engaged in times like this. And I was just wondering if you had some idea about where the break information related to motor system and all these things be stored. So are you expecting the motor system to be one of the key components that store information for, I mean, say,
danger
response to the environment, or would you consider more output systems to interact with model systems?
Yeah.
Having more active role, so that
yeah, or be more the output or the everything. Yeah.
Component and so what?
Yeah. So we're actually testing this. So yeah.
Sorry about
Yeah. Yeah. I mean yes. So yeah. Yeah.
Involves some of the sensation story involved.
Yeah.
But in this case, I'm not really sure.
Yeah. 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 But it's what we want to test. Like the last experiment of the grant was to test this. So yeah. But I'm not gonna answer yet.
Now, how long it lasts? I mean, I'm not sure that it's. I mean, that will also be interesting. Whether you can review police, if you can reinstate.
Yeah. Yeah.
How long they remember? I'm not sure they remember. You know, reinstate.
Yes.
Did we need reinstatement here?
No.
No.
Yeah. Okay. Okay.
Any other questions?
Okay. Think we can wrap it up for today.
Yes, so thank you.